Welcome to this primer on functions. In this lecture, we'll look at the notion of bijective maps, which is a central notion in all mathematics. And let us recall a few things that we need. So first, we will recall what is the power set of a set X. So if X is any set, then the power set of X is the collection of all subsets of X. So let me write that down. Okay, and it includes the empty set. So that's something that we need to keep in mind. And what about this thing? So here alpha and beta are just any two numbers, even complex numbers. So recall that this expression is nothing but what I'm going to write. Right? I'm sure you can agree. And the next one would be right. And similarly, you can expand this out. So in the first time, you will get a negative sign with sum of all the things that you see here, then a plus sign, and then sum of product of two things, and so on and so on. Okay. Here are two problems for practice. And now let us get started with the material of this lecture. So suppose we have a function f from a set x to the set y. Then we say that f is a bijective function if it is both injective and surjective. Right? That's the definition of a bijective map. It's both injective and surjective. So here is a picture where, of course, you can see a function which is injective and surjective. And the philosophical point is that f you can think of as a device which changes the names in the set x and changes the names in the set x and produces new names. It just changing the identities of the points in x in a way so that the information is preserved. Whatever information was there in x is still preserved because it's after all not losing, it's not identifying two different things, and everything in y is associated with exactly one element. So that's the philosophical point. It's okay if you don't fully grasp what that is trying to say at this point. And one more piece of terminology is that bijective maps are also called invertible maps. So that's just terminology. Okay. All right. So now we have the notion of inverse of a bijective function. So now if we have a bijective function, what we can do is quote unquote reverse the arrows. Right? So we had this arrow and we reversed it to get this arrow. We had this arrow which we reversed to get this arrow. So you can reverse all the arrows and still get another function, which is this time from the target of f to the domain of f. And you can do this precisely because f is a bijection. For instance, if f were not a bijection, and in particular suppose that it was not an injection, meaning it was not an injective function, then you would have two different points in the domain mapping to the same point in the target. And now if you reverse these arrows, what you would get is this point is now getting associated with two different points here. And hence this wouldn't anymore be a function. So injectivity is certainly necessary. And surjectivity of f is also necessary because otherwise some points would remain hungry here and that's not allowed. If you have a function, then the domain of the function should have every point in the domain should have some point in the target that it maps to. All right, so we can just formalize what we just said in words. So if we have a bijective function, then the inverse of f is defined as the map G from the target of f to the domain of f, which takes a point little y and y to the unique to the unique element in X, X such that that's the notion of inverse. So basically, it's just formalizing the arrow reversal thing. You just find the arrow that is getting into Y and reverse it. That's all this is saying. I'm sure you can correlate with the picture. And as a point of notation, the inverse of F is denoted by this symbol. Okay. So we just we just write F and put a superscript of -1 to it. That's the notation for inverse. And there was something I wanted to note, but now I forget what it was. Yeah, I forget what it was, so I'll remove it. So that's the notation. And a cautionary point. Suppose we had any given function f from x to y, then the pre-image of any set S contained in the target is written like this, right? So to recall, what is this? This is all the points in the domain which map inside S under F. So that is the notation, and this symbol may confuse us to think that F is an invertible map or a bijective map. It's the same thing. And this is just an unfortunate clash of notation, nothing else. This confusion somehow does not arise. Whenever you see this expression, it should not mean that F is invertible or anything. And that's all I can say. It's just that I agree that this shouldn't have been the case, but this is the case. It's just bad notation that we have chosen to work with. All right, so this is the end of this section. Let's move on. So let us continue. We want to look at an application of this notion of bijection. So what we will be doing is construct an interesting example of a bijection. But to get there, first we need to go through some more concepts. So suppose X is a set and A is a subset of it, shaded here. So this is X and that is A. Then the indicator function of A is defined as the map the notation is 1 sub A, and it is a map from X to 0, 1 or R, whichever. I mean, you can write whatever you like there. So I will comment on that, but for now it's the target is this. So this indicator function is defined as so if little x comes from the set A, then you output 1, otherwise you output 0, right? Basically it is encoding the same information as the set A. It's just a different way of looking at the set A. Okay. And one could also define the indicator function as, maybe a different color would be a good idea. One can define the indicator function as going from X to that. And it's the same definition, ditto same definition. It takes 1 if X is in A and 0 otherwise. Right? Most of the times this is more convenient for the reason we will see, but this is also fine. This is a fine definition, and it will be the context that will inform what we are using. Okay, I don't think I need to say anything else here. Yeah, okay. So let's make a very interesting bijection between the power set of a set and this set. So what is this set? This is the set of all the maps from X to this 2-element set. So let me write that down. right? That's the definition of this thing. Okay, and what is the identification? So let phi from power set to this be defined as phi of a is the indicator function of a for all a in the power set, meaning all subsets of x. So that's our map. Takes a subset of x and outputs the corresponding indicator function, and we claim that phi is injective. That's a very simple claim. So say phi a equals phi b. So before we continue with this, if suppose a were the empty set, the indicator function of the empty set is supposed to be the function which takes the value 0 everywhere, right? So I just wanted to say that. And now let's continue. So suppose phi a equals phi b for some a and b subsets of x. We want to show what? We want to show injectivity of phi, which means we want to show that a and b are the same. So let little a in a. So before I write that, so thus the indicator functions are the same. And now let little a be in a. We will just show that it is also in b. And that's very easy. So now, since the indicator functions are same, they take the same value on little a, which gives 1 is equal to this, which implies a is in b, right? If the indicator function of b takes the value 1 on a, it just means that a is in b. So what we did was we started with some arbitrary element of capital A and showed that it lies in b, and therefore what we have shown is that a is a subset of b, and similarly one can show b is a subset of a, and hence a and b are the same. So that shows injectivity of the map phi. And now for surjectivity. So this I wouldn't be doing in full, but here is the main point. So to show surjectivity, we start with some arbitrary function in the target of phi, and let a be the preimage of 1 under the function f. So again, what is that? That is nothing but those points in x such that fx equals 1. That, and now one can easily show. So that is an exercise. So show that phi a is equal to f, right? So that's fine. One can easily do that. Before we continue, I just want to point out that when we have the preimage of a singleton, we usually do not write these curly braces. So we just write f inverse of 1, and it means the same as this, and this is the proper way of writing it. But a lot of people, and including me and everyone I know, writes we just drop these curly braces. Anyway, so phi is a bijection. It takes a subset of x and just changes how it looks. And this will be an interesting identification. One more thing I want to say is that, so we also will use the map capital phi, which takes this to maps from x to real numbers, which the map is the same. The map just takes a to indicator of a, but this time when we write indicator, it is valued in r. I mean, the target is R, not 0, 1. Okay, and this is not a bijection, of course. This will not be a bijection in general, especially when X is finite. This is certainly not going to be a bijection. But this is at the very least injective. So this map is an injection and the proof is the same. So what we will really be using is this map in our application. But it is definitely good idea to be comfortable with this identification. When we say identification, we say bijection. So this bijection between the power set of X and this thing. Okay. So let's take a deeper look at this object. This is again, what is this thing? This is the set of all the functions from X to R. Let me write that. Okay. And now suppose F and G were elements here. So they are both maps from X to R. So then we can define a few things. So then we can define F plus G. So what is F plus G? F plus G is a map from X to R. And how is it defined? F plus G of anything in capital X is defined as just the sum of the individual things. This is of course for all X, right? So this is the new function that we have constructed out of the old functions, which takes an input and just outputs the sum of the individual outputs. Okay, and this is why R helps. So if we had just written 0, 1 here, we would run into a problem because this value may be different from either 0 or 1. For instance, 1 plus 1 is 2. So then here we wouldn't be able to write 0, 1. We would have to write R, and hence it is better to just take a wider perspective. Okay, similarly, we can define the difference of F and G, and again, this is a function from X to R, which is the point-wise difference. Right? And now finally the product. So this takes a point X and gives the product of the two values. Okay, so we have these three constructions, and one can note this. So you have three functions. Here, of course, F, G, and H are in this set. So then this thing is equal to that thing. This is a function which is the product of the sum of the first two and the third one. And this is a function which is the sum of the product of these two things. And these two things are the same. The reason is very simple. You just feed it a little X on both sides and see that things match. Similarly, this is the case. So the addition that we define here and the multiplication that we define here behave well with each other. And the reason for this well behavior is the same reason as to why addition and multiplication behave well within the set of real numbers. It's just borrowing that property and giving us this fact. Okay. Now I had left some space here because I wanted to say something, but now I've forgotten what. So if I remember, I will come back, but for now this will be blank. Okay. So now we will get back to our identification. So this was our bijective map, which takes a subset to its indicator. So that we can rewrite. It takes a subset to its indicator. What happens to A intersection B? What happens to this? So I'm just debating whether I should write R here and change it to capital Phi. Yeah, let's do that. Otherwise, I might run into trouble. So this is R. This is capital Phi. So Phi is not a bijection, but it is an injection. Let's do that. So now A goes to the indicator of A. And what happens to A intersection B? Well, by definition, it is the indicator of A intersection B. But here is the point that you should note. This is same as the product of the indicators of A and B, right? When does this give you a 1? When you feed x to it. So if you feed x to it, you get a 1 if x is in A intersection B, which happens if x is in A and x is in B, which happens if 1ax equals 1 and 1bx equals 1, which happens if and only if 1ax, 1bx is 1, and that's why we have this equality. So that's very nice. Intersection becomes product in this under this map. That's amazing. Okay. What about the union? Union unfortunately does not become the sum, but it becomes something else. So it becomes, of course, the indicator of A union B, but that is the pointwise maximum of 1A and 1B. Okay. So what is this function? You feed, when you feed little x to it, it just gives you the max value between 1ax and 1bx. That's what it is. And you can figure out why indeed that is equal to the union. What about the complement? So complement goes to the indicator of the complement, but that is equal to 1 sub x minus 1a. Right? Just figure this out, why this is the case. And we may drop the subscript here, and it means the same thing as 1 sub x. It's just more convenient to drop the subscript. You can write it and that's not a problem. And now most interestingly, what happens to this guy? This is of course the indicator of this, but as we saw, it is the product of the indicators, which is this, which by what we recalled is equal to that. So either you use this remark, or well, you use that remark to open this out, and now you should be reminded of that formula that we wrote in the beginning of this product. That's all. So that's what is going on, and similarly you can play this game for 3 things. So before we come there, now what about the cardinality of A? So suppose x were a finite set, so everything here was a finite thing. What is the cardinality of A? The cardinality of A is this thing. This is the cardinality of A, and it should be clear why. One cannot, I cannot really explain this. Basically, the x's which give you a 1 are the ones which are in A. So every point in A gives you a count of 1. You add all of them, you get the total number of elements in A. And if x is not in capital A, you get a 0. So you're just summing 0 and that doesn't change anything. So cardinality also has a very nice interpretation in this new world. And now suppose I wanted the cardinality of this. This shows us that the cardinality of A complement intersection B complement is summation x in x 1 minus 1a plus 1b plus 1a 1b. And I always forget to write x. So that's what the cardinality is, because A complement intersection B complement is that guy, and you just feed x to it, you get this number. And that is nothing but cardinality x minus cardinality A plus cardinality B plus cardinality A intersection B. Right? So this should remind us of inclusion-exclusion formula, and it is definitely an avatar of it. And one can generalize this. So maybe I've written everything here. So now suppose we had n subsets of x. Then by the same reasoning, this is equal to that. And you expand it out like high school, it just looks like 1 minus alpha 1 dot 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 1 minus alpha n. So if you expand that out, you will get this expression and operate the summation on both sides. You get that the cardinality of this horrible intersection is this more horrible thing. But this is what the inclusion exclusion formula is. You can apply De Morgan's law here, and you can write the left side as x minus the union of these things, so cardinality of that, and it will look more like the inclusion exclusion formula now. So this is equal to the difference of that. Okay. So yeah, what was I saying? So this inclusion exclusion formula is just a consequence of this equation, and that's amazing. And think about the problem on derangement that we saw in the primer on sets that we discussed. Okay, so that's a very nice consequence, and yeah, I think that is it. So with this, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.